Welcome everyone back to my another tutorial. Last time I showed you how we can train a simple PyTorch model. So this was kind of introduction to PyTorch, where I show you how to train an MNIST classifier with convolutional neural networks, and we saw how to achieve pretty high 97-98% of accuracy. This means that it's very accurate, but that's pretty simple task because the MNIST has a huge data set and we can use it all. We don't need to worry about. So basically I covered how we need to download this data with a custom NumPy functions, how to preprocess it, and how to convert this into batches. And then I show you how we construct our neural network model with convolutional neural networks and how we print the summary of it. And then how we optimize, how we define optimizer, the loss function. We constructed a train function and a test function to train it and validate on our data. And finally, I show you how we can save it on disks. And we train it for 5 epochs. Right now, it will be different tutorial. As I said, I will be working on a wrapper. This means that I constructed a PyTorch wrapper that right now my machine learning training utilities that are available on PyPy, and you should download it and install if you're running this tutorial. So basically this is 1.0.1 version, and this will handle both TensorFlow and PyTorch implementations to use. So, but for PyTorch I needed to do way more than with TensorFlow. I had to construct the whole model handling, metrics handling, callbacks handling, and etc. So let's begin. Well, it's way more easy right now because in the future it might fit with any architecture of the models we use. We simply need to preprocess it a little differently every time. So if I open my 7th tutorial, it's train, I minimize this, and we go to the beginning, for example. So this means here I am preprocessing the MNIST data in the same way I'm downloading it and saving on disk with two datasets data. But what I did here differently is that I use my machine learning training utilities library. And as you can see here, there's a torch where I import the data provider, model, accuracy, metrics, few callbacks that I show you how easy it is to work with them. And let's cover first how everything looks like. So here we simply preprocess the train dataset and test dataset. This means that we reshape it, that each element in our training, for example, dataset would have an image and appropriate target for this image. This means the MNIST label. And preprocess do this for both training and test. Then I implemented this preprocessor function. This means that it expands one dimension in our images and normalize it by 0 and 1 to have it as float instead of integer 8. So then in that same manner as I did in TensorFlow, I create a data provider, and here we pass our training dataset, we give it preprocessor, this means this function, and we give it a batch size, and this will automatically handle us with data. We can iterate this through and it will feed us the data. We will go into this later. So first, this uses multiprocessing or multi-threading node to do this on single core to faster thing for us. So then we construct a network the same as before, and then we define optimizer and loss functions, all the same as before, as in previous tutorial. So if you haven't watched it before and you are new to the machine learning with TensorFlow, I recommend to watch it. You can find it on my YouTube channel. Next, this is a custom one. You don't need to worry about this, but this is specifically for GPU, CPU training. And as you right now can see, this is a very similar manner as we can see in a TensorFlow. We define our callbacks. As we know that the PyTorch by itself don't have this kind of stuff as early stopping or model checkpoint callbacks. So I had to write them by myself, and then we feed our network to this kind of custom model object that will handle us the training and validation steps. Of course, before we were calculating the metrics as accuracy in a this validation step, and right now I simply need to give these metrics, its accuracy metric, and that's it. And then we simply call the model fit the same as we did in a TensorFlow, and we train the model. As you can see, right now I'm not saving the model. This model checkpoint callback saves it for me. Sorry for that, I was wrong. So I haven't forgot to do so. And here to the fit function, we feed the train data provider and test data provider, and we train for 100 epochs. But we'll see that it's never trains for 100 epochs because the early stopping callback hits a flag and it stops training and saves the best model for us by validation accuracy. Before that, of course, we can simply train the model and you'll see the results. Okay, let's go. I'll run this on GPU to make it faster, so my video recording might be a little laggy, but you can see it started training, and when it's training, we can clearly see the loss and accuracy of the training process, and when it finishes, we might see the accuracy. Yeah, that's right, the accuracy is here, and we can see the validation loss and validation accuracy is pretty high. And that's automatic. We don't need to worry about the training loop. And this might work with any model, whether it's object detection, whether it's image segmentation, it's text prediction, sound prediction, or whatever. It doesn't matter. And simply we need to work differently with our data providers to pre-process that data differently. And of course, we need to change the network to accept different inputs of our different data. And yeah, we run kind of this simple code, and it does the work for us. So right now, let's wait it to finish, and we'll come back into the details. So as you can see, my training model stopped, and the early stopping flag worked because model wasn't improving for 3 epochs, and my patience was here as 3. Of course, we could train this for longer, but we don't need to do so because, well, why wasting our time? Because it already achieved almost 99% accuracy. Of course, we can set it as 10. It would be 99.5% accuracy or even higher. Who cares? Well, this is for you, simply to teach you how to use this module. And of course, I'll publish this on my YouTube. There will be text version tutorial, and you might test this by yourself. So basically, let's begin from data pre-provider, data pre-processing. Let's go in. And this is kind of specific for PyTorch because you can see these modules are in a Torch stuff. And here I have the data provider, transformer, and augmenter just for typing to know what's need to be fed into this object. And basically, this is kind of simple object, the same as I have in my original machine learning training utilities data provider, that it's purely with NumPy. And what's different here that I use multi-processing here and workers, because originally TensorFlow has implemented this by itself inside his fit function. And this means that we need to construct this by ourselves. But it's pretty simple. We construct this thread pooling executor, whether it's threads or CPUs, and we start it. And simply we call a get item function each iteration. And this feeds this kind of batches to our threads working in the background, and it returns us a NumPy results. And that's everything what we need to know. If you want to get more details, you can go inside this data provider. And you might ask why I'm not using, for example, PyTorch dataset. Well, I want this to be flexible, that it would work in the same manner whether it's TensorFlow or Torch with this data provider. So And also we can use a custom preprocessing augmenters, transformers, or etc. Functions to our data provider. So this will let us handle all the data set easier for us. So this means that here at the output we receive a NumPy stuff instead of tensors. This means that we can implement even the, for example, we want to investigate what data we have. So we give it a custom function here, for example, show image, and implement CV2 show function inside to it. And it's pretty easy. And it will when we iterate our trained data provider, it will show us what images we have. If it's object detection, we apply these detections to our images so we know it's correct. When we are implementing some kind of augmentation stuff, when we are rotating, etc., it's way easier to debug our functions, what we are doing. So next we go to our network, and basically that's the same as before. It's pretty simple neural network that is handling simple convolution layers. Let's go back. We define the optimizer and loss. Here we set our network on CUDA, and you might know that in PyTorch, if we are setting our network on the CUDA as well, we need to set our data on CUDA because, well, it's trained on a GPU. But I wrote it so that my model is handling this stuff. It checks on what device is our network and automatically puts our data on this device. So let's go into this model, and it's pretty standard model. We feed model, optimizer, loss, and metrics, and here we use them, we save them, and here is a metrics handler. So this is a custom object that calls a metric whenever it's needed. It handles all these metrics, and then we have a stop training flag. We check on what device our model parameters are, so it's on CPU, GPU, or whatever it is. And so we check a validate step to check what the type is of our optimizer and model, because in Torch they need to be a specific type, otherwise it will not work. So next, there's a function that puts our data on a CUDA device, or if it's not, if it's on CPU, that's totally fine, we skip it, and that's it. Then we have a train step, the same as we use in TensorFlow. So here we have the same steps as showed in previous tutorial. We do the optimizer, we have received the output, we calculate the loss, and we do the backward propagation and do the optimizer step. And that's it. Then we need to update our metrics with target and output. And here we calculate the accuracy that you can see here. And we do this whether it's training or validation step, it doesn't matter. Then we have a very similar test step where we also simply get the outputs of the model, calculate loss, and update the metrics. That's it, we return the loss. So if you have some kind of different architecture, something hard, you might create this kind of object that inherits all the stuff and replace train step and test step, and you don't need to touch anything else. It will be handled for you. So next, there is a train step. And as you can see, there's my data provider that we created before. It's like a generator or iterator of data. And here we define that our model is in a training step. We create a progress bar here, and here comes the callbacks. We first, before we begin the batch, we call this callback, whether maybe we have some callbacks that needs to do specific stuff on the batch beginning of training. And then we simply check what type is data. So here originally comes the NumPy batches, so it automatically converts this Torch stuff, and then it places this to my GPU device, and this data then is simply fed to the model on the train step, we get the loss, and then we simply calculate the mean of the loss that is used for metrics to update. Well, originally metrics don't have some kind of loss update, but that's the best way where we might do this. And as you can see, we metrics and the training is true. And then from these metrics, we construct the description simply, and we update this description to our progress bar. So as you can see, for example, this line is constructed with a description, and we simply set our progress bar to have it. And that's it. And when the batch is finished, we call another function on batch end. And then after all the batches are finished, this means we simply finished an epoch, we call the metrics reset function. And this is our data provider. And it has a specific also function on epoch end. So whether usually this means that we want to shuffle our data when we finish our batch, and that's it, and we return the logs. In the similar manner is the test step. Well, we put our model into evaluation mode, and when we iterate our progress bar with our data, and yeah, we do this the same on batch begin, on batch end, and we calculate the loss when we push data to our model, and we update this with our progress bar, and then it's received in our metrics, and then we call the self metrics reset, and that's it. And then we need to shuffle our validation data for, well, it doesn't matter. Well, it's not necessary, but well, it's good to do so. So next, there's an additional function that might be changed in the future. It's a torch save, and it simply saves the weights of our dictionary from our PyTorch. And this is simply a state, and this is usually used when we want to load the model up and test how it works. And there comes the fit function. That's the main function that handles all the training stuff. And as you can see, we need to fit it with a train data provider and test data provider. We set how many epochs we want to train and what's the first epoch. And that's it. And then is callbacks, because callbacks are usually fed when we are using fit. So here they are, and here is a custom callbacks handler that handles these callbacks for me and for you, of course. And then we set on train begin with the callbacks and on train end, and that's it. So next we can see that we are iterating for all the epochs we have. We simply create a range, and then we simply call the callbacks. We call the train step with all the data in our train data provider, and then we call the test. And we merge the training logs with validation logs together, and we push them to the callbacks on epoch n. And for example, when the epoch is finished, we check the results of validation loss, validation accuracy, simple loss, training accuracy. It's up to us what we want to track and what actions we want to make on these steps. And these callbacks can change this top training flag. So this means if this callback sets the training off, it changes the flag of this kind of parameter, everything stops and it breaks the loop. And we go to another callback on train and we simply call the logs. And that's it. That's all the training loop we want to do. And of course, if you are interested, we can go to metrics, for example. And here we have a basic class for all metrics that you would need to follow if you are creating your own metrics. And for example, here from these metrics, I created the accuracy metric, and what it must have update and results functions. And here in update, we simply increase the correct and total values, and at the results, we divide the correct by total and we get the accuracy. And of course, when we call the reset, it resets the values of our parameters to the initial state. And that's it. And I believe that in the future, I'll create way more of these metrics to use. You'll see, you might use it later. So let's go back to the model. If I go to the callbacks, there also, I can remove this. There's also the callback. And as you can see, this has a lot of basic functions on train begin, on train end, on batch, on test, and etc., etc. And we need to do specific things on these functions. So when we are creating one of them, we need to do in a specific place. We want to do specific, for example, math stuff to calculate. For example, if we do object detection, we want to calculate mean average precision at the end of batch or validation batch, and we get the results how our model performs. So for this, I created an early stopping callback, as you might see, and we originally are tracking the validation loss. We have the patience, verbose, and the mode. And simply what I do here, I have on train begin. So I simply initialize the 0 values, what I need to do. And yeah, that's it. And then on epoch end, I'm calculating whether it changed. So this means within these logs, it comes the values, for example, validation loss and validation accuracy. And I know that what I'm trying to track, for example, in this case, this is monitor and monitor validation loss, and it gets the value of this loss, and simply it checks whether it changed, it improved or not. And if it improves, it simply quits, updates the value, and waits for another epoch to end. As you can see, for example, right now, I don't need this to do anymore. For example, it stops the training of the model. And the same here on train end, it simply tells us that early stopping flag worked, and we need to quit the training and stop it. So that's it. And the similar is with our model checkpoints, and I'm tracking everything, what I'm tracking, etc., etc. On train begin, I initialize the values, and that's it on train begin. On epoch end, what I'm doing here, I'm checking also whether I need to save the model or not. And as you can see, I'm saving the best model and wait for next epoch. And here's another save model custom function for this callback, and I'm saving the model. And that's it. So in the same way, we can implement the tensor board on an X conversion or anything you need. So that's it. As you can see, it's pretty easy. I implemented all of these, and I also created a lot of different tutorials. And if you were tracking or following my previous tutorials, you might see that the same structure I'm using, whether it's TensorFlow, and right now it will be a Torch, and pretty easy in blocks to train our model. We don't need to re-implement all the training loops from zero again, whether it's training, it's testing, we won't forget anything if we need. So this means that we can follow within the same structure, whatever project we use. So I decided to begin this with MNIST because it's pretty simple and it's easy to track the errors and etc. And right now, as I finish this, I will be able to apply this kind of stuff to my other previous tutorials, for example, capture to text or handwritten recognition, and I will need to re-implement similar model as I use in TensorFlow, and I will be able to use all the same architecture to train my model, and it will be pretty easy. You'll see I'll come with this in my next tutorial, and you'll see that it's pretty amazingly simple to use this kind of library with the blocks. I'm using the same architecture of blocks in my work stuff that I need to do every day, and this is the reason why I started this kind of library, because I'm tired of re-implementing everything from zero, all the training steps, validation steps, or etc. So I decided to hold everything in one library, this one, and it's as easy as doing ml2u pip install, and you have everything you need. And that's it. So as you can see right now, it finished training and everything is working pretty fine. We see the accuracy, and our model is saved into this kind of checkpoint. And if I open my models, where's my models? I have it here, and here is my models weights saved from the PyTorch model. So right now what I need is to go to my test. This test is exactly copy from my previous tutorial, except I changed the path where my saved model is. And right now I can run this, and it will be pretty easy to use. So I initialize this, run this, and it works out of the box, and you should see few examples of MNIST detections. As you can see, it's 7, it's 1, it's 0, 4, 1, 4, 9. I don't know. It will be, I think it will be very hard to see a mistake, because our trained model is close to 99% accuracy. So we will need to check at least 100 of our images to find where it did mistake. And that's it. As you can see, it works, and it's out of the box. You can train any model you want. And I go back here, and what I thought to do is that before I made a lot of tutorials, image to word, capture to text, handwritten recognition, and etc. And I think that it would be really valuable to re-implement one of these models to Torch. For example, if I take handwritten recognition, I have here a model in TensorFlow. So this means I will re-implement the same architecture of the model into PyTorch, and we'll try to train this in the same manner as we did here. So if I open the train Py in TensorFlow, as you can see, I also changed everything here to work with my new release of refactoring. Here I implement all the same stuff from ml2u TensorFlow. And if I go down, I also use the same callbacks: early stopping, model checkpoint, train logger, TensorBoard, reduce learning rate, and etc. So I need to implement a few additional callbacks as model to NNX for PyTorch, reduce learning rate, for example, TensorBoard, so we could track this on TensorBoard, and we will have the same kind of working stuff as we did there. And you can see the fit actually looks the same, except that fit here had workers in this place, and I'm having these workers on a dataset provider. So it's a little different, but that doesn't matter. I achieved the same results as this one. So that's it for this tutorial. As you can see, I showed you how easy it is to use it. I'll publish all my code into GitHub. I'll write a text fetch tutorial in details. I don't know if I'll cover this in such details as I covered in this tutorial, but you definitely can read it. I lost the sound here, sorry. So basically, I covered everything I wanted, and probably that's the end of this tutorial. I hope this tutorial was useful for you, and you don't hesitate to subscribe to my channel, like this video, share it with your friends, comment if you have any questions or suggestions, or you can raise an issue on the GitHub. So thank you again for watching, and of course, we'll see you in our next tutorial. I'll try to make it shortly, not wait too long, and we'll see where it can be improved in the future. So thank you again for watching, and see you next time. Bye.